We're ready for a deep statement that is going to serve as our replacement for the mean value theorem. It's a statement that describes the approximability between the derivative on the one hand and the difference quotient on the other hand. Now, one is the limit of the other, and so we expect them to be related, of course, but this gives us a strong control over how tightly they're related. So let's look at the statement. We're going to start with a function which is continuous and differentiable, and the derivative is going to be continuous as well. And that's on some open set U, which is open in the real line or in the complex plane. Notice that an open subset of the real line would not be an open subset of the complex plane, so that's why I'm kind of allowing it to be in either case. Then we're going to let K be a compact subset of that open domain on which the function is differentiable with a continuous derivative. And then we have this statement. So before we dive into this statement, let's just look at this picture. Supposing we have a point z0, which is the center of a delta ball. Okay, so we have a point z0, any point z0 in the compact set K. And we're going to draw a delta ball around it and hope that that ball is also contained within the set K. Now, if we have a point W and another point Z, which are both of them close to z0, then we can use them to form the difference quotient, f of W minus f of Z over W minus C. If they are close to z0, then the difference quotient between Z and W will be close to f prime of W, which should also be close to f prime of Z. And so we would expect this difference quotient is approximately equal to f prime of Z0. But it's not so easy to prove that it's approximately equal to that because it's not just the limit definition, because Z and Z0 are different, and W and Z0 are different, and so it's not just the definition of the limit, but we would expect that difference quotient between W and Z to be close to the derivative f prime of Z0. So notice that these are all values of our function Q here, right? This is Q of WZ, and this is Q of Z0, Z0. So what this statement says is that, yes, you may approximate the difference quotient by the derivative. In fact, it is possible to obtain control so that the difference between the difference quotient and the derivative is less than epsilon. So the first thing you should notice is for every epsilon, and then we're asserting a control over the relationship between the difference quotient and the derivative. Now, these conditions are perhaps not surprising. These conditions simply say that for some value of delta, that W is close to Z0, that Z is close to Z0, and that W is not Z. I have to assert that W is not Z, otherwise I can't have my W minus Z here. So these three conditions really just say that this is the right picture. This picture is really what's going on, right? W and Z0 are close, Z and Z0 are close. W is not Z, so this sentence makes sense. What's surprising about this and what makes this a powerful result is that the delta is quantified before even the Z0 is quantified, before any of these are. And that's what makes this a uniform approximation here. Basically what we're saying is for every epsilon there, so you want some epsilon approximation, then like uniform continuity, we get a uniform power. We can choose the delta up front. And then that delta applies to all the scenarios across the compact set K. It applies equally across every picture like this to all Z0, W, and Z, so long as these conditions are met about them. And so that makes this a very uniform approximation tool, and that's really where its power derives. Now, in order to prove this, we have to put some pieces together. There's not much to prove. So let me point out what we know already. So we know that Q of WZ is continuous on K, right? Because f prime is continuous, and we've recently proven that therefore Q is a continuous function of two variables. Actually, I misstated that, and let's state that correctly. This is a function of two variables, W and Z, and so it's continuous on K cross K. And we know that K cross K is compact, because K is compact and the product of two compact sets is compact. And so, we know that K cross K is compact. We also know that a continuous function on a compact set is actually going to be uniformly continuous. And so what this entails is that Q of WZ is uniformly continuous on K cross K. And that must be a powerful condition. And so let's write down what that means. So what that means is for every epsilon, there exists a delta so that for any two pairs of points, so that is for any two, now I want a single point in k cross k and another point in k cross k. So the initial point is going to be w naught, z naught, and the next point is going to be wz. So for any, basically, two pairs of points in k cross k or 4 points in k. So if the distance between w naught and z naught, if the distance from the first point to the second point is less than delta, it's not a delta, that's a d. If the distance between this point and that point is less than delta, then the distance between q of w naught, z naught, and q of wz will be less than epsilon. So this is the direct statement of the uniform continuity of q. Not the continuity, but the uniform continuity. And notice what makes it uniform continuity is that the delta is quantified first before any of these points are quantified. Now, this is what we know from the abstract topology because we have a continuous function on a compact set. Does it get us what we need? Well, very close. Actually, let me reverse this for clarity here. Let's say q of wz here and q of w naught z naught here, because it'll make it tighter to this. So the first thing we need to question is, what do we mean by the distance between this and this? Well, there are various metrics that can be applied to k cross k, but the simplest metric that we can consider is the max metric between these two. So this thing actually can be interpreted to mean w minus w naught is less than delta. That should be modulus of that. So that can be interpreted to mean that is less than delta, and also z minus z naught is less than delta. So this distance between 2 points in the product space and one point in the product space and another point in the product space being less than delta can be interpreted to mean both of these conditions. Now, does this entail this? Well, yes, but we actually need to take what's given here and we need to specialize it. Notice that here we have abstractly q of w naught z naught, whereas here we have f prime of z naught. And so what we need to do is we need to say, okay, let's just, if this is true for all w naught and z naught, let's just apply it when w naught equals z naught. And so basically I want to say, whenever w naught is equal to z naught, if it's true for all pairs w naught and z naught, then it certainly is true for those pairs where w naught is equal to z naught, okay? Now, when I specialize it that way, this magically becomes q of z naught, which is the same as f prime of z naught. Now, this thing magically becomes a z naught, which makes it consistent with this. This thing was okay already. And now, the only difference between what's stated here and what's stated here is, well, I guess there are two differences. The difference remaining is this one has the assumption that w is not x. And this one has generically q, but this one has the difference quotient. Now, so all I need to do now is I need to specialize this a little bit further to the case where w is not equal to x, right? So w is not equal to z. And if I have the case where w is not equal to z, then this thing has to be equal to that thing. So basically, what we've done here is we've taken the straight-up definition of uniform continuity of the function q, we've specialized it to when w naught is equal to z naught, which gets us these conditions, and we've specialized it to when w is not equal to z, which gets us this condition and gets us the ability to simplify this to its difference quotient. And then everything that it says is just becomes this line. So this demonstrates that we can uniformly approximate the difference quotient with derivatives, or vice versa, if you please. And this is a powerful tool that we will use basically everywhere one would have used the mean value theorem. We can get this similarity between the derivatives and the difference coefficients as much as we like.